Hi. Okay, so the first topic is the security of block ciphers against exhaustive key attacks. By exhaustive key attack, I mean the following brute force attack. Given a few input-output pairs, so think of chosen places attack, when adversary has a bunch of messages and gets back ciphertext. So the adversary knows this relation between a bunch of points, MI and CI. And we want to ask how long does it take to find the key K if we want to exhaustively search for it? Of course, okay, it takes the key space, right? You have to search. So for example, for this, you have 56 bits of a key. So it's a 2 to the 56 possibility for the key. But the issue is, okay, let's say you find a key. How do you know it's the correct one? So let's argue that if you have enough of these pairs and you find some key that matches a given M to a given C, then with only a tiny probability, it could be that this is not the correct key. Okay? Because just because you found some key that maps M to C the same way as you've seen the challenge encryptor do it, it's not a guarantee that perhaps you found a different key that maps the same plaintext ciphertext pairs. Okay, suppose that the block cipher is an ideal cipher. Now, what does this mean? This is a new concept, a new type of analytical way to look at what a cryptographic building block provides. Namely, that every key is like an index to a random function. So an ideal cipher means that, so a standard assumption about PRP security is that a challenger, so here is a two people game. Here is a challenger who picks a random key, and here is an attacker who sends a message, gets back the PRP output, sends another message, gets a PRP output, and interrogates this challenger on any number of messages. And the attacker's goal is to distinguish outputs of a PRP from outputs of a true random permutation. But the challenger picked a key at random. So, for example, this, in the case of this would mean that the challenger uses a true uniform random key. Here in the ideal cipher scenario, you say something stronger. Not only for a random key, an attacker who interrogates this box cannot tell this function from a random function. For any key, even for a key chosen but known by the attacker. So that's kind of crazy because, well, can the attacker not locally run this circuit on any key? So it's not a random function. So what the assumption really means is that talking to a desk software, you input a key and you input a plaintext block. And if you don't look what's inside of the desk software and just see the output, then as far as you're concerned, every efficient algorithm of this type that just talks to desk as a black box would behave the same way if you replace this desk black box with an even blacker black box, namely one that doesn't have any desk circuitry. And for every key, it creates a random new permutation on the appropriate blocks for the appropriate input domain, right, which is the block size. So it's as if this was this 2 to the 56, because that's how many keys there are, family of independent random functions. That's a much stronger thing than just saying no efficient attacker can distinguish a box that chose a random key for itself from a permutation. So this in particular means that even if you gave this box a very weird key, like all zeros, the DES circuitry is still going to perform fine on these keys. And if you talk to a DES like a black box, you still cannot tell it from a random function. You can replicate its behavior by running DES code on an all zero key. But again, if you're talking locally to this type of thing, you cannot tell this box from a random function. So it is not really an assumption that DES is an ideal cipher, because anybody who knows, you cannot say, oh, consider people who are ignorant of DES circuitry and therefore are ignorant of the fact that it is not a random function, and you can locally compute the same algorithm. So it's a deterministic algorithm. It is not really an assumption. It is you consider a class of attackers that do not look at that circuitry. Okay, if you took such idealized view of a block cipher, then indeed the only things that one can do is to I see M and C, so M1 C1, M2 C2, and now I can locally search for key K and run this as a black box on the key K and M1. See if it outputs C2. Run it on M2 and key K and see if it outputs C2, etc. Okay, and if this is an idealized cipher, so it's a random permutation for every key from 264 to 64. That's the domain. But then still with an overwhelming probability, if you get an MC pair, then there exists only one key K, which explains this MC pair as in a correct encryption relation. Okay, and that holds with the probability 1 minus 1 to the 8. Where did this come from? It's a simple counting argument. You take all functions from 64 bits to 64 bits, permutations, and you look at how many keys there are. And look, the probability that there exist 2 keys that map the same C and M pair to each other, both of them explain the same plaintext ciphertext pair, is upper bounded by well, the number of K primes and the probability that there is a collision, that the key K prime output the same ciphertext as key K on this message M. But if this is a random function, that for every key K, so basically if this instantiated is a family of 2 to the 56 independent permutations, then therefore des K and des K prime are 2 different permutations which are both random. So the probability that they collide is 1 over 2 to the 64, right? On any M, this is a random 64 bits, and this is random 64 bits. So, and then you just take a union bound over all keys, and you see that this already gives you an upper bound that is 2 to the minus 8, right? And then if you have 2 pairs, 2 plaintext chosen, so in other words, the probability, if you find a key, given a single pair, if the probability that you find a key that maps them correctly and it's not correct key is only 2 to the minus 8, right? Well, that's maybe not such a tiny probability, but once you make it 2 blocks, then it goes down to 2 to 71. Okay, why is that? Because on 2 blocks, basically, I can think of this. So this is a random number. This is a random number. Now there are 128 bits in C1 and C2. So to ask that des k and des k prime both create the same 128 bits, it's even stronger thing, right? So you get 128 divided by 2 to the 56 again. I mean, it's it's 128 minus 56. Okay, and so therefore, basically, 2 message ciphertext pairs are more than enough to say if you find a key that maps them correctly, then you can rest assured that it's a correct key. Okay, so challenges against DES or any other block cipher are phrased as, okay, we have a few blocks that are public. So this is M1, M2, M3. And we publicize the ciphertext. So we choose a random key and we encrypt. And then we give one more ciphertext that encrypts an unknown block. The solution to the puzzle to the challenge is this plain text. So how is it broken? You find a key K, which makes its correspondence correct. And we have seen now, if you find such a key, then it's a tiny possibility only that that key is not correct. And then you simply use this key to decrypt. Okay, so that's the solution to the challenge. So a long time ago, these searching 2 to the 56 size space of possible DES keys and performing DES operations on all of them took significant amount using distributed resources. Then a single machine was built that cost with significant cost, but it would speed up this to just 3 days. So this shows that you shouldn't use it for banking. Somebody can invest $250,000 and basically destroyed all encryption of a bank within a day, and that was 20 plus years ago. So then more sophisticated algorithms to combine the power of this machine with internet search, and they basically, there was a certain chase to distribute this search into and to optimize its execution, and with the programmable arrays, and right, so it basically was a sweet spot of relatively inexpensive but yet powerful hardware that was optimized for this massive computation of DES tests. And it cost not very much, and it destroyed it quite quickly, and that was almost 15 years ago. So this basically shows that DES you cannot run. It's too weak. The brute force search, and this had nothing to do with any cryptanalysis. So how come, well, because all asymptotic claims about security of a block cipher construction of a PRF based on PRG, encryption based on a PRF, none of them mean so great, if you instantiate them with two small security parameters, where the concrete bounds involve terms like 2 to the size of the key. And already this fundamental bound, which is 2 to the size of the key, turns out to be insufficient for this circuitry and for this security parameter. So you cannot use, it is not trivial to write a code that searches through such space fast, but it is possible. So there were two ways that the community went from this. People realized that 56 bits is too small. In fact, 56 bits were chosen by NSA as, not strong enough so that NSA cannot break it. But the being able to break your own codes is a source that can cut both ways, right? So NSA tools leak to other agencies, and so other agencies can come up with their own attacks. So you cannot have rely on security of a banking system whose keys are of that size and are subject to these attacks. So there were two things that happened. First of all, the question was, basic question is, okay, let's come up with a new version of DES, something that is natively has longer keys and gives us more security. Indeed, crypto community worked on, and people proposed many new block cipher designs, and then there was a competition for the new standard. AES, the advanced encryption standard, won this competition and basically became a new standard for encryption for the block cipher. But another way was, okay, we don't see any inherent vulnerability of DES except for its low key size. Can we use DES in some sequential way so that to artificially increase its key space, namely, for example, use two DES keys always, and always encrypt under the first key and then encrypt under the second key? Well, so now your effective key is 2. And in order to brute force search, you have to find 2 of these. So now the key size is 56 plus 56, 112. Well, you're not gonna search through that anytime soon. Let's talk about that idea. This key extension of to larger key sizes, the standardized method for this is called triple DES, and it's basically triple any cipher. So you can apply it to DES, you can apply it to any cipher. So let E be a block cipher, and define triple E as a block cipher which takes keys which are triples of the keys of the underlying block cipher, and they use the same message space, right? So they go over the same message space, and the triple E, using a triple of keys K1, K2, K3, is defined like this in a message: run encryption in a forward direction using key K3. Take the result and do not re-encrypt it with K2. No, run decryption algorithm. So it's the same DES box, but it's a DES inverse box, right? So every block cipher must come with block cipher going forward and its inverse. So some way of running the circuitry backwards to map from cipher to a message. So we run a decryption box with using K2, and given the result, we run encryption again for this, right? So this is this DES once, DES2, DES3, now with key K1. Why go encrypt, decrypt, encrypt, and not encrypt, encrypt, encrypt? For one reason only. Because if you standardize it this way and you make the keys equal, then you get backward compatibility with a single usage of DES. So for testing for this backward compatibility, it was chosen because there was no belief that putting E here instead of D would change the security of this construction in a new way. But doing it this way allowed backward compatibility. So now the triple DES has 3 sizes of key. So instead of 56 bits, you have 168. It's also 3 times slower than DES, but DES was patented, in the late 70s. So this is very, very simple circuitry. I mean, simple. It's a fast circuitry that was feasible then. So, increase of computing power is much more. I mean, what we could afford in the 70s, we can definitely afford doing 3 times that much now. So that's not a big one. But the basic thing is like, why 3? Why not 2? Right? So, and that the fact that you have 3 keys, does it really mean that the best brute force search had 168, has to search through 168 bits? In other words, that the best attack is 2 to the 168. No, the best attack is much faster than that. It's 2 to 118. So let's look why. And the basic thing to look at is, first of all, let's look why not 2 DES. Why 2 DES, really double DES, doesn't really increase security of DES. So this would be a double DES, a double E cipher. Its key space is a pair, and you use these keys. First use K2 in the forward direction, take the result, and then you use K1 in the forward direction. Okay, pictorially it's like here. So key length is 112 bits, which is great because that will be hard to brute force search. However, there is a better way to attack, and it's using this middle point of the circuitry. So the search problem given M and C is to find K1 and K2 which satisfy this. But how about change this circuitry like this? Let's find K1 and K2 such that EK2 applied to M, which is this red dot, is equal to inverse of E, in other words, D, with K1 applied to C. So this equation. In other words, it's a form of a meet in the middle attack. You're looking for points which could be created this way and also could be created that way. If you find a collision between these 2 arrows, you basically succeeded in finding K1, K2 that makes this, that satisfies this. So why is this faster than a brute force search? Because you can split the job like that. Let's say you build a table of possible red dots that has 2 to the 56 entries for 2 to the 56 possibilities of K2. So you encrypt, these are all the possibilities for this wire, for the 2 to the 56 possibilities of K2. And then you have this table, and you recourse on all K1 possibilities. So 2 to the 56 choices, and for each of them, you decrypt C, and you check if the decryption is in any of these, is in somewhere in this table. if you found a collision, then that's the key K. Your key K is K1, and the row, the key in this row is your K2. So basically you're done, except from the, so how long did it take you? Well, actually, to perform this test, you have to sort them first, because otherwise, look, what was the time? It took you 2 to the 56 to create this table. Okay, and now this loop, if this test was looking into an unordered list, then just this test would take 2 to the 56 steps of checking each equality here. And 2 to the 56 multiplied by 2 to the 56 will give you the trivial bound, 2 to the 118, 112. So, so you have to sort them. So 2 to the 56 to build the table, but to sort it, right, using any n log n sort algorithm takes n times log n. And then once you search, when you sorted them, then the search is a binary search. So it takes logarithmic time, right? Because you build the table, it's sorted, and for every key here, right, you compute this possible dot. Now you have to test, is it or is it not in your table? Well, that's a binary search, so it takes log of how many entries are in the table. So so that's where you get the 112, because I mean so so the time of this is about 2 to the 63. It's 56 times the log here, which is, well, 56 is like about 2 to the, well, it's about 64, right? So it's 2 to the 6, right? So 56 plus 6 is 62, and then you have 2, another factor of 2, right? Because you're using it twice. Now, so the time, you know, if 2 to the 56 brute force was possible already years ago, then you only, you know, how much slower is this? A factor of 100, and that's not enough, right? A factor of 100 is not enough. In 16 years ago, where the brute force search was already possible, you cannot. That doesn't give you a guarantee of security. So the thing that makes it slightly impractical is the fact that it takes space, right? To make this table, I have to store it somewhere, and this is a bigger, you know, bottleneck of this attack. On the other hand, you know, you can distribute it, right? So it is still possible. It wouldn't be easy to program this, and to, you know, this will be a major programming task to create this, to make this attack really, to show the feasibility of this attack. What the triple test does, though, is that it says, okay, let's not bother with this. Let's not place our security on such shaky ground. Let's increase the block size. I mean, sorry, let's do one more. Let's do one more layer of keyed encryption. So, and the best known attack against this essentially runs just like this attack, but finds here the vulnerable point. So it uses the same space, right? Because you have to create the table of 2 to the 56 possibilities. But now, going backward, you have to guess K1 and K2. And and that is that is 56 times 2, right? So that's 112, and plus the logarithmic factors for binary search and sorting. Well, the sorting not really, because it was in this term does not dominate, but for binary search, right? So hence from 112 bits you went to 118 of security. So that's why triple DES. Now strengthening DES by doing triple DES is not the only possibility. So here's a less, I mean, it's somehow intuitive, right? That, well, if I have 3 keys, how do I use them to strengthen encryption? Well, use first key, then a second. Basically, this is called cascade construction, right? Re-encrypt your message with another key, right? So pictorially, if you have 3 padlocks, right? How do you strengthen security, right? You use one, and then the result you use another, and the result you use another on top, right? But here's a very different way. You use one of the keys, in this case K2, to encrypt. The other 2 keys are just pads. They're not really used as a proper key in an encryption. The key K3 is used to as a sort of a permanent IV, if you will. Remember CBC mode? What did you do? You took a random IV and you XORed it with the plaintext block, and fed the result into a block cipher. Here, you have a fixed key that you use to XOR every plaintext before you feed the result into the block cipher, and then you have one more key. So the block cipher output is not the ciphertext you output. You post-process it by XORing, by treating K1 as an output pad. So this is called an input pad. This is called an output pad. And your key K1 and K3 are just these pads. How can such a trivial thing as using the key to just XOR? So this is, we have seen this in one-time pad, right? That's what you do in one-time pad. You take a key and you XOR your plaintext with it. But here it is not a one-time. You're using this key K, and you're going to encrypt, millions of plaintext blocks using it. Always using the same pad on the input, and a different pad, but always the same one on the output. Why does this improve security? Well, you can analyze that it does if E is an ideal cipher. So if you treat E as black box that uses K2, okay, to index which of the 2 to the 56, in the case of DES, random permutations it will instantiate with, and then you process your plaintext by the simple XOR with another key, and you take the ciphertext and again you simply XOR them with another key. Then for every choice of K1, K2, K3, interaction with this box is like interaction with another random permutation. So the result is like talking to another instance of a random permutation. The key length is different here, because in the case of this, K1 and K3 are actually longer than K2. This is 56 bits, and K1 and K3 will have 64. So it's even better because you have more keys. But is there some attack, like attack against the triple depth? So actually there is. And these attacks are not so hard. Like they are basically generalization of the attack on triple depth. So in particular, okay, what I expressed here was like the hope for what this construction you would like it to be. That for any choice of K1, K2, K3, it is another random function, but it is not the case. There is some weaknesses of this construction. However, still effective key length is longer than just K2. Interestingly, if you give up on one of these keys, so you either skip the output pad or you skip the input pad, you would not, that would not increase the effective key length at all. So just doing input or output would have no effect on security. Doing both has a funny effect of increasing the security not by the sum of the bits that you put in, the 64 for the input pad and the 64 for the output, but for half of that. So the nice thing about this is that, so this is actually slightly better than for JSX, and it is faster because the circuitry just takes a single execution of this, and it's also backward compatible. If you make K3 and K1 all zeros, then the result is just this. So it satisfies all the requirements, and it just was not adopted as widely because, again, like I think because the triple dash just seemed more complex. So this is what I said already, right? And that I will put as a homework, because it's not that much harder than the picture you've seen before. If you start looking what's going on, you will see that there is easy attacks on these. So this does not, there is other ways to do it. We will get to see them also later. So let's look at this question. We said, okay, if you had this pseudorandom function, then you could use it to encrypt, and you have randomized encryption that is secure when you use the same key to multiple messages. And the simplest way to do it was randomized counter mode. So where do PRFs come from? Well, I'll show you that you can get a PRF from a PRG. And this was, I think, Goldreich and Micali in the 80s, maybe 84. Okay. Here is so recall that the counter mode of a block cipher operation, that if you have a PRF, then you immediately get a PRG. Just run a PRF on consecutive strings, on consecutive integers, for example, and they're all pseudorandom outputs. So you just concatenate them, and it's a pseudorandom string. And you can go any however far you want to. This is, as long as this is polynomial, you can do it. What about the other direction? So, well, so let's say that you have a PRG that is very strong. So it takes n bits and it creates really an arbitrarily long output. Let's take, think of D as like fifth or seventh power. Okay, so if your input has 128 bits, right input, then the output will be 2 to the 128, 2 to the 8, or say 256 bits of input, right? So the output is 2 to the 256, which is 2 to the 8, to the power of 7. So this is 2 to the 56. It's a huge number. Okay. Still, and let's say so that you compute all of this, and you try to use this G to create a PRF. You divide the output of the PRG into n to the d blocks, each of them n bits. That's why I set it to n to the d plus 1, so that I can parse them this way. And let's say that that the output of the PRF on argument x is the xth block. Okay, in this PRG output. So on argument 1, this is the first of these blocks. On argument 2 is the second, etc. Well, first, it's not an efficient computation, because if I want to compute a block index with 1,000,000, I have to run this huge PRG just to get there. Basically, it's a linear time. Like, so if I want to, so yeah, this is not going to be very efficient. And the blocks are too small for any practical use, because how many different arguments can I have? Well, only from 1 to n to the d, but n is a polynomial. So how many bits can I fit into these x's? Only this many, right? Because it's the logarithm of the number of these blocks. So this domain does not have, my x's are not, the length of x's is not polynomial in n, it's logarithmic in n. And that is not great, because remember, the block size of the PRF was very important. Like, for example, randomized counter mode. How did I encrypt M? I had to choose a random nonce, so X would be random from its range, and I would encrypt M under FK applied to R. And the security of this was tightly related to the probability that I ever pick the same two nonces R, and therefore this would be rerun, and basically I would use this one-time pad twice for the two different messages. So it was the number of queries square over the size of the domain of the PRF. But if the domain is essentially polynomially sized, right, because there's only n to the blocks, then this is already insecure for Q, which is square root of that. So even if this was some humongous thing, like you know, n to the 6th, okay, then after n to the 3rd queries, you're going to have an overwhelming probability of collision. So you can only use it n to the 3rd. It's inefficient, and you can use it only for very small number of times. Okay, so that's not an efficient construction. It's not a general purpose construction. You can say, well, but maybe that's a good place to start. So I have a PRF on short blocks. Maybe I can use it to create PRF on longer blocks. But similarly to how I said a PRG that extended just a little bit, could I somehow run it again and again to create a secure PRG that creates much larger strings? Can I similarly increase the block size of a PRF? And these are not known. I mean, I will effectively show you one way, but there is no generic moves like that that are going to be faster. So let's see this construction. So hold on. So you know, how about running a PRG and just treating an output as okay, how about shortcutting the whole thing and running a PRG on key K and a plain text block concatenated? Okay, why is that not the simplest PRF? So if the answer is no, this is an insecure construction. Intuitively, if you assume G is secure, this means that on a random seed, it behaves in some good way. But in the security experiment of a PRF, the K part of the seed is random, right? It's a key. From the PRF perspective, it's a key, so it's randomly chosen. But this part of the seed is not random. Adversary decides it, right? Remember, here is the challenger who picked K, and adversary sends any X it wants and gets to see Fk of X. So this is if this is how you construct it, then what adversary sees is an output of a PRG on a seed whose left side is chosen at random in a good way, but whose right side is not random at all. It is whatever adversary wanted. So that's one intuitive problem. You're not seeing outputs of a PRG on random seeds. The right hand of every seed is non-random and chosen by the attacker. There is another problem, which is that PRG is okay to see its outputs if every time you see it's seeded with a new random seed. But here it wouldn't be. This key K was chosen once, but then for every X, this key K was the same. So it's like seeing a PRG applies to related seeds. The seed at every case, its left-hand side is always the same key K. Again, that should ring a warning sign that the PRG should not be used in this way. And in general, it's so if you see this, how this differs, how the usage of a PRG within this PRF construction, what kind of usage will subject the PRG to, then you can see not hard to show that there is some PRGs that are obviously insecure if you run them in this way. Okay, so for example, what do we say the weaknesses are? We said two types. That first of all, the X part of the seed is determined by the attacker. So let's consider an PRG that essentially ignores part of the left side of the right, the right side of the seed, and therefore it's going to have the same outputs no matter what X adversary gives. And therefore, the view of these outputs would be clearly distinguishable from a view of random functions applied to different X's. So let's take a secure PRG and say that we just run this PRG on all the bits here of the seed, K concave with X, but with last bit chopped off. So now this would mean that if you take it on two different seeds whose last bit differ, then this new PRG has the same output. So just take two X's whose last bit differ, but all the bits before are the same. Then Fk on X will be the same as Fk on X prime. And of course, a random function would collide on these inputs with only negligible probability. Okay. You will have this type of exercises where you are trying to see, okay, is this particular usage of a PRG an okay thing? This is the type of blueprint that you should look for. Here is a weakness. Here is the way that this usage would basically create a non-standard usage of a PRG, and the counterexample. Indeed, precisely, it is non-standard because there is some PRGs that is going to fail. This construction it will create something attackable. Okay.
Professor? We could also do what we did last time, right? Where you redefine G in a negligible sized set. So you could make Fk0 be 0 always for every K.
So what's the other attack? So yes, okay, in general, I'm sure you can find many attacks in this. So this is definitely not the only counterexample.
Yeah, my idea is to take G and then you change it so that if X equals 0, all 0 bits, then it outputs 0. This will still be a PRG.
Yes, it will still be a PRG because you changed its outputs on a single seed. That seed has there's only negligible probability that the random seed would have the right-hand side all equal to zeros. Yes, so that will be another counterexample. Very good. Okay, so here is the Ggm construction. Let's say you have a length doubling PRG, and we actually have seen the first layer of this construction already. You define a PRF on a single on a single bit argument. So the key is n bits, and the PRF takes an input, which is a single bit, and outputs an n-bit string. And how? It applies the PRG to the key k. It creates a string of length 2n, right? Because the G creates outputs of 2n when you give him n bits. And let's call the first block, the left side of this output GK index 0, and the right hand side GK index 1. So this will be a PRF on key k and input 0, and this register is a PRF on key k and input x equal 1. And this is a secure PRF. Why? Because basically without loss of generality, adversary can ask, well, give me the value at 0, it gets this register. Give me a value at 1, it gets this register. And under PRG security, these are distributed like indistinguishable from random to random strings. So how can we do it over larger domain? Well, recurse. So run G once, get 2 n-bit strings, parse it as left and right, and then apply G to the left one, parse it into left and right, and apply G to the right one and parse it as left and right. And let's call this row G1 of k, and the PRF value on a 2-bit argument will be G1 of k indexed by the block. So I take the block, I treat x as an index that shows me which block of G1 of k to output. And again, without loss of generality, adversary just gets all 4 blocks on 4 different arguments. And we already argued that this is a secure PRG. We argued it a few lectures back. So this row is indistinguishable from a random string. But you can, so this is the arguments that we had. So we had this argument already. Why this 3 ways, 3 G's form a new PRG from n bits to 4n bits. But now you can extend it further. And basically you build a binary tree, right? So adding one more layer creates a 3-bit PRF. And you can recurse this argument. In general, you can do it for polynomially many times, because to evaluate, so here is the output of the PRF. This block is the PRF output on argument 101. And this block can be computed only with 3 operations of G. This one to compute this register, one more to compute this one, and then this operation to compute this one. All the other parts of this tree do not have to be computed. So it doesn't matter that there's tons of stuff to the left and tons of stuff to the right in this binary tree. The only thing you have to do is to follow from the root to the leaf and compute G at every moment you go down the tree, right? The binary tree. So if you do it n times, so this is a binary tree of depth n, it will cost you n applications of the PRG to create the PRF output. But you see now that the block size is not such a big issue. I can, if I want larger block size, so larger, I just have to go deeper into this tree. Now, but still, this is rather expensive. So it is feasible. This is basically often not how PRFs are constructed in practice. So the PRFs inside of DES and PRFs inside of AES are not following this procedure. But just making shortcuts in it. So this is the general construction, right? This is, you follow down the path from the root to the leaf of the tree. The topmost register is your key, and then you recompute registers along the path by successive applications of G to the previous register, and taking either left or right block of the result, depending on the bit of the argument. Okay. So now now how is it is instructive to see the proof of security for this, because it doesn't exactly it is not fully implied by this the same arguments that we have seen before for the PRGs. So for the depth 2, it was a hybrid argument that replaced the top with fully random strings and then replaced each of them in the end, yes, through this hybrid of 3 steps, argued this whole output is indistinguishable from a random string. Now, if this tree has depth n, then this bottom row has length 2 to the n. So if I try to argue that all this bottom row is indistinguishable from a random string, that would be nonsensical, because this bottom row has exponential size. So it makes no sense to ask that the bottom row is indistinguishable from a random string for any polynomial attacker, efficient attacker, because even the input has exponential size here. So what do I do? Well, in the security argument, which is written, and you get a pointer from the syllabus to the section in the Katz-Lendl book, what adversary sees when he asks for x1, value at x1, value at x2, value at x3, he chooses indexes in the last row. That's his x's are the indices into the last row. So even though this whole thing has exponential size, what in any run with a polynomial attacker, what you need to consider only is some chosen polynomially many indices from the last row. Each of these indices is going to create a path from the root to that index. And this path is going to collide, in particular, they meet in the same root, right? But there is polynomially many of them. So the total number of registers that you have to consider is the number of these leaves, number of queries, so Q, which is polynomial, in N, and N, which is the length, the depth of the tree. So you're looking only at Q times N registers, which is polynomially many. And now you do this argument over a subtree that has depth Q and sorry, depth n and a size q. Okay, and it looks like copies of this thing, but only for those many points. Okay, so that's why it creates a hybrid. You effectively make q times n of these steps, and because that's a polynomial, that creates a security argument. Okay. So it is a generalization of the proof you have already seen. Well, so okay. So we see that the PRG can be used to construct a PRF. But PRF is so for every key. So now is okay. You're choosing a random key, and adversary asks you for polynomially many of these leaves. You give it to him. You can compute, given your key, he gives you index of the leaf. You compute it for him and give it to him. And these leaves are indistinguishable from random points, and therefore the whole thing is indistinguishable from a random function. But how about making it a block cipher? So how about creating some way to invert? So now the ciphertext is the content of the register, and the plaintext is the path, because X determines the path down which you go to reach this register. So how could you invert efficiently? Somebody tells you what's in this register, and now you have to recover the path. There is no efficient way to do it. You will have to scan through the whole thing to test which one is it, and give a path. Well, that's exponential time, because there's 2 to the n registers in the bottom row. You cannot do this, but also you don't guarantee that there exists no collisions here. In fact, if this is really like a random function, then the collisions will exist here. There's no reason to believe that this is not going to collide anywhere. There is exponentially many objects here, and the size of them, so there's 2 to the n, actually times 2 of these registers, and each of them is just size n. So there is going to be a galore of collisions. But that does not affect the security argument, right? But it does affect your ability to invert this. So it's not very clear how to go from a pseudorandom, how to extend this so that to ensure invertibility. But there is a beautiful general tool for converting PRFs, which is functions that scramble input and don't know how to invert it back from, to PRPs, pseudorandom permutations, so functions who scramble inputs and yet have some magic way of going back. And it's a very simple circuitry called Luby-Rackoff, called Feistel permutation. And Luby-Rackoff showed that that permutations, sufficient number of rounds of that permutations imply pseudorandom permutation. So you know what? Let me do this next time, because I'm a little bit going slower. So so let's just cut test actually contains the circuitry inside it, so it motivates its construction, but we are now concerned with a general thing about the circuitry, that it converts any PRF into a PRP. Here is the Feistel network, Feistel permutation. Given a PRF and I'm hiding key sizes, okay? I'm just like, whatever key sizes there are, the inputs and outputs of a PRF is n-bit blocks. Then I can create a PRP, so an invertible scrambling function that will use twice longer blocks. So its blocks are of size 2 to the n, 2n rather than n. How do they work? I take my inputs to a capital F, and I split them into two halves, the left and the right. And what I do with them is the following. Okay, so first of all, I have this PRF family, the small f. Small f is a PRF. F1, F2, F3, Fd, they're all the same PRF, just indexed with a different key. So if I have depth d of Feistel, I need d keys to use for each of them, right? So the first key is going to instantiate F1, the second key will instantiate F2, etc. And each of these is a map from n-bit to n-bit. So I take my input, I take the right-hand side, and I run the first PRF, so PRF with the first key on this register, gives me n bits, and I XOR it with the left side of the input. And I take the result of this XOR, and this is my new right block, whereas my old right block simply gets copied as my new left block. Then I recurse. I use a new, the second permutation, PRF, in other words, the same PRF, but with the second key. And I do the same circuitry as did before, but just with the new register, left and right, using the second round function. And so on, I do this for d rounds. Let me first show you that this computation is invertible. Well, that's rather easy to see. Okay, and what is my final output? These registers. So LD, RD is the output of the capital F. This is the input, these two, of capital F, and this is the output of capital F. How do I go back from the output to the input? Well, I use the left side of the input of this. I have these two registers, so I parse it as left and right. I take the left and I apply the last round function to it. I recompute this wire, and I have this wire. XOR is an invertible operation. So I XOR these two wires, and I get back this register. And this wire is very simple. I make this a copy of LD. So I just take this and copy it here. And so I went from the D round registers to registers at D-1. So of course I recurse this and until I get to the input. If you look at the circuitry, it's actually the going it backward and going it forward. It's actually identical circuit. All you do is that you replace the order in which these permutations are done. So rather than starting with F1 and ending with FD, you go backwards. In other words, the circuitry is the same. Okay, so that's the recursive procedure in a short form. Here is the Luby-Rackoff theorem about this. It is that 3 rounds of these Feistel permutations, if F1, F2, F3 are 3 instances of a PRF with 3 independent keys, then the whole thing is a PRP, meaning that you should know what a PRP is, but I'll repeat. If the adversary is faced with the following experiment, the challenger picked key of this 3-round Feistel at random. The 3-round Feistel key is a triple of keys, 1 for F1, 1 for F2, 1 for F3. And then, okay, so now these round functions are instantiated with random keys. An attacker chooses the first argument, call it x1. It's an argument of 2n bits, so it defines the value of these registers, the left and the right side of the input. And what he gets back is these registers as the output of the 3-round Feistel applied to his input with these 3 round functions. He doesn't get to see these intermediate values. He only specifies the input and gets back outputs. And what Luby-Rackoff shown, that 3 rounds suffice, that if adversary has only this, I specify the input and I get back the output interface to the circuitry, and he can run it again and again. So he can specify, having seen an output for some input, he can now specify a new input, perhaps related to the previous one, perhaps reusing some values that were created here as output. And he says, okay, what's the output on that? He gets back new value of these registers corresponding to the new argument he stuck in here. And he adversary recurses. If he has polynomially many queries, he cannot tell any of these outputs. He cannot tell this whole circuitry from interacting with a random permutation. Okay? So that's the Luby-Rackoff claim. And an instructive thing about this is to look at, well, why 3 rounds? How about doing only 2? So what would happen if, but that is sort of, it's not hard to see that that is an insecure construction of a PRP. In other words, if R2, L2 was your output, then there would be an efficient attack, which would show values of these registers, and having seen the output, and perhaps recursing a few times, would distinguish, would have like an efficient and a simple test that distinguish interacting with the box that implements 2 rounds of Feistel on totally random PRFs F1, F2, from interacting with a random permutation. You know, and even easier cases to look, okay, how about the single round of Feistel? Well, that's sort of obviously not the right thing, because this left-hand side of the output is simply equal to the right-hand side of the input. So this register output part is a copy of the input. the right-hand side of the input. And this is clearly distinct from a random permutation. The probability that the left-hand side of the output equals the right-hand side of the input for the case of a random permutation would be 2 to the minus n, where n is the size of the blocks. How come 2 rounds have an attack? Well, you can look for sort of a weak path through this. It's either this path or it's this path that connects inputs to outputs, or this input to this output. A way you can look at these vulnerabilities is, remember, an attacker against a PRP chooses these inputs any way he wants, gets back outputs. Now he can choose them in some way that perhaps takes these outputs into consideration, perhaps not, but definitely can take previous values of these registers into consideration. Let me give you an example. How about asking this circuitry to execute on 2 values of these, such that the left-hand side is the same in the 2 executions, just the right-hand side changes. Then there will be some possibility of correlation between them. Actually, let's look at the other case, like when the right-hand side is the same, the left-hand side changes. Then the fact that the right-hand side didn't change between the 2 inputs meant that this F1 acted on the same register in both cases. Therefore, this wire was the same, right? So perhaps something about this XOR can be correlated between the output and the input. Once you see this correlation, you would be quite impressed that, like, the next round completely eliminates this correlation. This will not go over the proof for that. It's slightly more complex. It includes conditions on cases of all sort of events here that form some sort of collisions and correlations not happening. It's not that complex. I forgot how detailed the proof of this is in the book, but I believe there is a sketch of this proof at least in the book. And of course, there's other write-ups also. Another thing that I'm not mentioning here is that in a block cipher analysis, for example, for CBC analysis of security of the CBC mode, you need something stronger than pseudorandom permutation. In a pseudorandom permutation, adversary can only specify inputs and get outputs. In something called strong pseudorandom permutation, he, in addition, can specify any output, and the circuitry would compute the inverse function and give him the input, the corresponding input. So in other words, the box that he talks to doesn't implement just EK, it also implements D index with the same key K. And he can talk to both. So he can ask EK to go forward, and then, well, if he feeds the same thing into DK, he gets back what he started. But ability to go ask the box to give you both the forward direction computation and the backward computation might be stronger. And if you cannot tell interactions with EK-DK versus a random permutation and its inverse, then EK-DK is called strong pseudorandom permutation. 3 rounds of Feistel suffice for for this to be PRP. But if you want this to be a strong PRP, then again, actually, there will be an attack. So this being able to go both forward and backward, adversary can detect that he's not talking to a random permutation and its inverse. He's talking with to a 3 rounds of Feistel and its inverse. However, 4 rounds of this is a secure, strong PRP. So just slapping one more round stops these attacks, and probably the result is a strong permutation. So even if adversary can ask this box to give you forward and backward on any chosen inputs outputs, he cannot tell this from a random permutation and its inverse. Okay, so that would be it. I will release a new homework where a bunch of problems that I already said would be on it. And if you have questions, go ahead and ask them. For next time, we'll do DES. We'll look into DES circuitry, and which in particular has Feistel inside it. And then we'll look at strengthening encryption security to CCA security. Okay. Okay, so if there's no questions, I'll close it now. I'll stop recording.